estimating, put that on the outside, and then solve it and answer the questions accordingly. Okay. We definitely want to do one more of these for sure. As far as numbers are concerned, anybody have a question on what I did here? As far as the actual calculations? Okay. Well, we'll do another one which will help. Now, this next problem I want to do, well, let me just, that's what I was going to say. We're going to do a decay one. There's some interesting things happening in number 7 here, so I'll do number 7 on the board as well. Let's just take a second to initially read the problem. It says, plutonium-238 with a half-life of 86 years is used as a compact source of electrical power in many applications, ranging from pacemakers to spacecraft. Suppose a power cell initially contains 1.6 grams of plutonium-238. Predict the number of grams after 20 years, and then finally, when will there be only half a gram left? Okay, a lot of things were said there, so let's go back through this thing and see what order they were said. Plutonium-238. What does the 238 represent? The type of plutonium has no bearing on this problem whatsoever, except to confuse you and make you think you have to put the number 238 somewhere. It's just a name, okay? Kind of like a car, you know. Well, I won't go into detail, you get it. Sometimes numbers are just parts of the name. This is the case. So plutonium-238 has a half-life of 86 years. What is that? What part of this problem is the half-life of 86 years? That is our observation. In 86 years, the amount will be reduced to a half. You see, that's a hidden observation. It doesn't say, in 7 days there was 140 aphids. It confuses you. It says it has a half-life of 86 years. In other words, in 86 years, when t equals 86, the initial value is cut in half. That's an observation. And it comes before we even get our initial amount. It talks about what it's used for. Again, fluff for the problem. I don't care what it's used for. I need to know what the initial amount is. What is the initial amount? Okay, so here we go. We start our problem. We have the initial amount of 1.6 grams. Be very careful of the units, although in every problem in here, I believe the units are all the same. Don't ever forget that units could be different. In other words, they could say the initial amount is 1.6 kilograms. How long until there's 0.5 grams? And then you'd have to create a conversion of grams to kilograms. We're not going to deal with that in this class. That's a physics and chemistry type question, although we can handle it in math class. Let's get the math down first. Then we can worry about unit conversions. And so on this problem, you should be pretty straightforward. All the units will be the same. So I don't even need to list them. Basically, I know that my initial amount is 1.6. Okay, so now I can start writing the model. The amount at any time is equal to the initial amount, so I know it. What is it? 1.6 e raised to some growth rate or decay times t. And in this case, we know the r is going to be decay. So when we solve for r, should we get a positive or negative value? Negative. Okay. As of right now, I cannot put in my question, which is how much will be after 20 years. If I put 20 in for t, I still don't know the rate. I can't do anything. So I need to start out first by putting in this observed value that, well, first of all, t equals 0. We have our initial amount. Then t equals 86 years. I have, well, half that amount. Right? That's what it means by a half-life. In 86 years, there's half that amount left. If I put this into the equation, I have 1.6 divided by 2 is equal to 1.6 e to the r times 86. I know it takes 86 years to get to half the initial amount. And if you look at that equation closely, you'll see that 1.6 on both sides of the equation. So it can be canceled away and written as 1/2 equals e to the 86r. Just divide both sides by 1.6 and that whole part of the problem is gone. Remember, the half-life is good for all initial values, so the 1.6 is not unique here. So really, whenever they give you a half-life, you can immediately write 1/2 is equal to a to rt and solve for it. Just put in a t that they give you for half-life, and you can always find r. So it's a nice little trick. But if you don't see that trick, certainly you can see half the initial amount, and then multiply both or divide both sides by 1.6 to get this equation. exactly what you do on the board. We're not done though. What does R equal? ln of both sides. So you get the ln of 1/2 is equal to 86R. And then finally, to find out what R is, we divide by 86. So R is equal to the ln of 1/2, the whole thing divided by 86. And this had better be a what? Positive or negative value? Negative. And quite frankly, it better be pretty small in that sense too, in absolute value. Because this thing's decaying, it takes 86 years for it to get halfway down. So the decay rate, is it going to be big? Yeah. As far as absolute value is concerned, it's pretty close to 0, don't you think? So let's see what happens. ln of 1/2 divided by 86. Negative 0.0081, we round up. So now we have the ability to write our full model here. The amount at any time t is equal to 1.6 e to the negative 0.0081 times value of time. And that model can be used to answer a variety of questions, namely, how much after 20 years? Well, let's see. That's going to be a of 20, which is equal to 1.6 e to the minus 0.0081 times 20. Let's talk about this though. It takes 86 years for it to get down to half of 1.6. So at a mere 20 years, are we going to be anywhere near half of 1.6? We should still be, well, relatively close, probably like 1.2 or 1.3, right? Not down in below 1 yet. So keep these numbers in your head so when you're doing this, things make sense. And we have 1.6 second e to the negative 0.081. Yeah, 1.36. That seems reasonable, right? We started out at 1.6 grams. It takes 86 years to get down to half. So after a mere 20 years, it should be down just a little bit. It's down 0.3 grams. That makes sense. Okay. Then the last question is like, okay, so how long until it's down to 0.5 grams equal to 1.6 e to the minus 0.0081 times time? Okay, 0.5 grams, that's well past half, right? Half of 1.6 is what, 5.3? I mean, 0.8, excuse me. Sorry, 0.8. So 0.5 is well past half, so this had better be bigger than 86 years, right? Okay, so I can divide both sides by 1.6. You get whatever this is. I don't know, what is this in the calculator? What's 0.5 divided by 1.6?
0.312.
Okay, thank you. Is equal to e to the negative 0.0081 times t, so that the time will be equal to the ln of 0.3125 divided by negative 0.0081. Hopefully bigger than 86 years. What is it again? Point what? I can't see over there. 143 years, to be precise. 143.6 years. What did the author have? I'm curious. For number 7. 144.3 years. Okay, so as you can see, now that we're running it out pretty far, 144.3 versus 144. Close enough, but all attributed to the fact that their growth rate is 8 decimal or 9 decimals, and mine's only 4. Okay, and we're going to stick with 4 for this whole remainder of this course. All right. Pay close attention to problem number 10. It is long, to say the least. Very good test material, number 10. The rest of these are good. The one with the striking light surface and all that stuff, you guys mess with that as best you can.